Hi everybody, this is Ms. McClellan here to go over IM2 Notes 1.1.1a with you. How can I classify this polygon? Now by the end of this section, we should have a greater understanding about the attributes that make various polygons alike and different. We will also learn vocabulary and notation that we will continue to use and build upon throughout our course. We're going to start with this little bonus problem, and hopefully it helps us understand symmetry, which is going to come up a lot today. And the bonus problem involves making a snowflake. So we start with a square piece of paper and we fold it diagonally in half. And then we fold it diagonally in half again. Diagonally? That doesn't really make sense for number 3, but anyway. And we fold it in thirds, trying our best to really get the thirds right. Then we cut. And the reason we've done that is to make a 6-sided shape. Seems like I've made more than 6 sides, but it's good enough. Okay. And now we just do what we want to do. A little cut here. Maybe a little cut here. Zigzag on top. You can do whatever you want. If you're doing this online, you don't really have to make your snowflake, but it's fun, and I'm doing it. If you are watching this video, it's probably because you missed class. And if you missed class, first of all, sorry, too bad. Missed a fun day, but anyway, we made snowflakes and we shared them with everybody at our tables. Okay, that'll be it for me. Let's unfold and see what my snowflake looks like. How was your summer vacation? Are you glad to be back at school? I love snowflakes. Okay, so the reason we did this was just to sort of see what kind of symmetry happens. Can you identify any rotational symmetry in our snowflake design? If so, describe the angles of rotation and the points of symmetry. And then, if not, explain why. So I'm going to see if I rotate my snowflake about its axis, how many degrees does it take before I'm in the same orientation? Okay. I'm in the same orientation. I'm in the same orientation again. Same orientation. Same orientation. Same orientation. Okay. So it seems like every time I rotate 1, 2, 3, 4, 5, 1/6 around my snowflake, I'm back to where I started, just visually. So first of all, yes, we can identify rotational symmetry, which we'll define later in the lesson, but it basically just means if you can rotate less than 360 degrees, meaning all the way around, if you can rotate less than that and end up with your shape in the same as its original orientation, then you have rotational symmetry. And for us, that's going to be at 360 over 6, because we only had to go a 6 around, so that's at 60 degrees. And we know because, well, this was a physical experiment. So we made our snowflake and rotated it to find out how far we need to rotate to get it back to its original orientation. Period. Okay, so what do you think symmetry is? Sim means same, and a tree means of shapes. In your mind, think about what the word together, symmetry, means. I'll give you a few seconds. Okay. Keep your thoughts in your mind as we go about today's lesson. And before we continue, we're going to cut out some shapes. So we have this polygon bucket, which you would have in person, but if you are online, there's a digital version, and I'm going to cut out the shapes, so I'll be right back. Yay, I cut out the polygon bucket. Let's continue. Next page. Okay. So we have an introduction to a polygon bucket. We're going to build the composite figures below and draw line segments on our shapes on our paper to indicate our answers. So using the shapes in our polygon bucket, let me build part A. Let's see. Ooh, I see part of part A. I think this shape will be part of it. Maybe right there. Okay. And we're going to have some trial and error, of course. That's what this activity is for. Maybe this shape. And then maybe my rectangle right here. Perhaps. Maybe that's not quite right. Maybe this one right there. Perhaps. Well, I've changed my mind. I think probably like this. And that. Oh, there it is. Yay. Okay. Let's draw the lines on our original shape. We've got one here. Here. And here. Okay, next, part B. Okay. For part B, I think I need my scalene triangle on the top. It looks like I need my parallelogram down here somewhere. This looks like the trapezoid perhaps right here, but I'm not sure. No, I don't think so. Maybe my rectangle should be here. Does that look about right? Okay. Still not sure what shape should be right here. Maybe my rectangle isn't right. Let's remove the rectangle. For our right trapezoid. Let's try the rhombus, perhaps. No? Maybe my parallel. I'm already using my parallelogram. Right here. Ha! Well, wonderful students. I just pressed pause for a little while to figure this out because I thought I remembered. Anyway, it turns out that the online version of this, which I originally made this lesson with, doesn't have exactly the same shapes as the ones that we cut out. So it wasn't going to work, but this is what the solution would have been. And I will make sure to update our printed version so that it works. So I apologize. And anyway, I will update our printed version. This is the shape that should have worked. Okay. Now we'll do part C. Hopefully part C works for real. Let's see. So for part C, I have, I'm pretty sure I need my isosceles triangle. And then I think that looks like a trapezoid, so I think it'll match up here. And beneath that, I see, it looks like my rectangle, as well as a friendly little, done this and this and this. So maybe I have a right triangle that will fit up there. Yeah, I know that this is what it's supposed to be. I think that the scale of my rectangle might be a little bit off. All right, we've got our shape. Now, what we just made was a bunch of composite shapes. Composite shapes are made up of sort of larger shapes made by combining smaller shapes without any gaps or overlap. Period. So these are called composite figures because they're made from putting together smaller figures without any gaps or overlap. So for example, this, for the purposes of our class right now, would have not been a composite shape. And I guess what I'm talking about when I say shape is in particular polygon. And this would also not be a composite shape because it's got some overlap. All right. Next, 1-3, moving right along. Venn diagrams. A Venn diagram is a tool used to classify objects. An item is placed in the Venn diagram in the appropriate region based on the conditions it meets. We have an example. Here we have condition 1 and condition 2. Items in condition 1 satisfy condition 1 in region A. Nothing from condition 2 fits in region A. In region B, both conditions are met. In region C, only condition 2 is met. And in region D, neither condition is met. We're going to draw all of our polygons onto some Venn diagrams now. So here we go. Condition 1 has at least one pair of parallel sides. Condition 2 has two sides of equal length. So I'm going to make a bigger Venn diagram so that you can see me work through this. Okay, so that's not much bigger. Parallel equal length. Okay. Let's just place our shapes. So first we have this regular hexagon. Well, this has parallel sides. All opposing sides of a regular hexagon are parallel because, for example, if I were to extend these lines forever, they would never meet. So it meets condition 1, parallel. These little tick marks mean parallel. It also meets condition 2. Since this is a regular hexagon, each side length has the same. A square is a regular square. Equilateral triangle is a regular triangle. Regular just means that all sides are the same length. So this meets both conditions. So I'm going to draw it right here between the two. Okay, square. A square has 2 pairs of parallel sides and all the sides are the same length. So a square fits in the overlap because both conditions are met. Okay, this is a trapezoid. A trapezoid by definition has a pair of parallel sides. This is not one of those trapezoids that has any equal length sides. So this only meets condition 1. It has a pair of parallel sides. Okay. A parallelogram. This is a parallelogram. It has 2 sides of parallel sides and opposing sides are the same length. So it beats both conditions. A regular pentagon. All the sides are the same length because it's regular, but a pentagon does not have any parallel sides. So I'll draw that right here. Isosceles triangle. Isosceles trapezoid. This has a pair of parallel sides and 2 lengths that are the same length. Isosceles means same length. Okay, so I'll draw that in the overlap area. All right, rectangle. 2 pairs of parallel sides, 2 pairs of same length sides. Rectangle. Okay, scalene triangle. This has no lengths that are the same and no parallel sides. So this goes on the outside because no conditions are met. Okay. Right triangle. This is also scalene. It's a scalene right triangle. Even though it has a right angle, it doesn't have any parallel sides, and none of the side lengths are the same. So it goes on the outside. Okay, isosceles right triangle. No parallel sides, but it does have 2 lengths that are the same. So this meets condition number 2, that 2 lengths are the same. Quadrilateral. This is any shape with 4 sides. And in this particular example of this shape, none of those sides are equal length. Hopefully that shows in my drawing. Kite. This is 2 pairs of same length sides, but none are parallel. Isosceles triangle. 2 sides of an isosceles triangle are the same length. Could mark that. Okay, equilateral triangle. 3 sides that are all the same length. Right trapezoid. It's a trapezoid, so it has parallel sides, none of which are the same length, so it only meets condition number 1. Parallel, 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 parallel. I'm not marking the ones in the interior because I think it would be too small. Okay, a rhombus. Rhombus is special. A rhombus is to a parallelogram, like a square is to a rectangle. A rhombus has 2 sides of parallel, 2 sets of parallel sides, and all the sides are the same length. This meets both conditions. Okay, next page. Part B. Now we're going to reclassify our polygons for the Venn diagram below. Condition 1 is that the polygon only has 3 sides, and condition 2 is that it has a right angle. All right, this has 4 sides and no right angles. Meets neither condition. Rhombus is on the outside. This has 4 sides and no right angles. It meets neither condition. Goes on the outside. This has 4 sides and 1 right angle. So it doesn't meet condition 1 because there's more than 3 sides, but it does have a right angle. Right trapezoid goes right here. All right, this is a quadrilateral, 4 sides, no right angles. Isosceles triangle. It only has 3 sides. Yay! No right angles. Isosceles. Equilateral triangle. It has 3 sides. It meets condition 1. No right angles. All the sides are the same length. I hope I called that equilateral. I feel like maybe I said isosceles. Anyway, isosceles right triangle. 3 sides. Oh, it has a right angle. It's a star. There we go. 3 sides and a right angle. Okay. Scalene right triangle. This has 3 sides and a right angle. Meets both conditions. Scalene triangle. No right angles, but it does have 3 sides. Rectangle. This has 4 right angles, more than 3 sides. Isosceles trapezoid, 4 sides, no right angles. Regular pentagon, 5 sides, no right angles. It goes on the outside. Parallelogram, no right angles, more than 3 sides. Goes on the outside. That doesn't look like a parallelogram. Should be clear that it has 2 sets of parallel sides. Trapezoid, in general, does not come with a right angle. 4 sides, no right angles. Regular hexagon, like a stop sign. How many sides does a stop sign have? I guess I don't know. Okay, regular hexagon has way more than 3 sides and no right angles. Square. My friend, my square. 4 right angles, more than 3 sides. Ooh, part B was easier for me. Not that easy is a good thing, but anyway, let's do part C. Yay! Okay, finally, let's reclassify the polygons for the new Venn diagram shown below. All right, this one is about symmetry. Okay, so condition 1 is that we have reflection symmetry. That means that if I fold the shape on it in half, it lines up with itself. So this is an example of something with reflective symmetry. And let's find one that doesn't have that. This is an example of something that doesn't have reflective symmetry because there's no way that I can fold it and have it line up perfectly upon itself. And number 2 is 180-degree rotational symmetry. So an example of something with 180-degree rotational symmetry is something where if I find a point, if I rotate this 180 degrees, it ends up in its same orientation again. All right, let's do this. Number 1 has reflection symmetry, starting with this rectangle. Well, yes, for sure. If I fold this in half, it definitely lines up upon itself. So it has reflection symmetry. And rotation symmetry, well, this was the one I used as an example, so yeah. This has both conditions. Right trapezoid. This does not have reflection symmetry or rotation. Yes, I could rotate it 360 degrees and have it line up right, but rotation symmetry is only when you can rotate it less than 360. So anyway, this has neither. I'm going to put it on the outside. It's a right trapezoid. Okay, this is a regular hexagon. It has reflective symmetry. See, I could fold it there. This is reflective symmetry across a lot of different axes. There are plenty of mirror lines here. Lots of places I could fold this in half. And what about rotation? Okay. If I rotate this, let's see, what angle was that? I just rotated it. What angle is this? Okay, all the way around my circle is 360. This is, how many times around the circle can I go? 2, 3, 4, 5. All right, so this is 360 over 6 degrees, so that's 60 degrees. This has rotation symmetry. I don't know why I found the, but does it have 180 degree? Oh yes, very good. So this has both. Rhombus. Okay. If I rotate this 180 degrees, so it's like that. Yes, it has 180 degree reflection symmetry. And can I fold it in half? Why, yes, I can. Do-do-do-do. A rhombus belongs in the intersection. Okay, what about a plain old trapezoid? Rotation? No. Folding? It's not going to work. Okay, what about a square? I hope you see that a square works. Look. Boom, square works. And I can absolutely fold a square in half and have it line up on itself. I'm gonna run out of space. Okay, parallelogram. Parallelogram has rotation symmetry, and you might be tempted to say it has reflection symmetry, but it doesn't, because if I fold this in half, it does not line up on itself. There's no way that I can fold this in half. So it only has rotational symmetry. Okay, isosceles trapezoid. Rotation? No. Folding? Reflection symmetry? Yeah, totally. It's got it. Isosceles trapezoid. The arrows mean parallel. The tick marks mean same length. Scalene triangle? Just no. It's got nothing. Goes on the outside. Isosceles triangle? Well, it doesn't have rotation, but I can fold it. Isosceles triangle. Well, I can't rotate it, but I can fold it. See? There we go. Perfect. So this has 1, but not 2. It has reflection symmetry, but not rotation. Okay. Quadrilateral, neither. Isosceles right triangle, I can fold it, but I can't rotate it. Kite. A kite can be folded, but rotation doesn't work. Isosceles right triangle. This has neither. Equilateral triangle. All right, I think I can do this one. 180 degrees though? No, it doesn't have rotation by 180 degrees. But I can fold it. And pentagon. 180 degree? No. Fold it? Absolutely. I can fold this right down the middle. Like so. Okay. So this has reflection, but not rotation. When you look at this, what do you think? I think, hey, maybe reflection is more common than rotation. Well, that was our last shape, so let's go to the next problem. These notes summarize types of symmetry. Now, when there is a rigid transformation, that's when you reflect, rotate, or translate. Translate is like sliding something across a page. And it appears to map a polygon back onto itself. Then we can call that symmetry. The figure is said to have symmetry. So for example, an isosceles trapezoid has reflection symmetry because there exists a line that you can fold it across and it lines up on itself. So a trapezoid has reflection, symmetry. Oh, and we have a word bank. And line L is called the line of symmetry. Okay. This snowflake right here has rotational symmetry. Because if you were to rotate it, for example, 1/6 around the circle happens to be 60 degrees. If I rotate this 60 degrees, clockwise or counterclockwise around its center, it maps the snowflake back onto itself. So I rotate this and nothing changes, nothing changes, nothing changes, nothing changes. That's true for any multiple of 60. So it works for 60, 120, 180, 240, or 300, etc. There are no polygons with translational symmetry, but this pattern has translational symmetry. And that's because it can be translated across itself. Lots of things have translational symmetry. They're pretty important in design science. So for example, this has translational symmetry. If I were to block off an area around the shapes, like so. You can't tell what part of the card you're looking at, and that's because it has translational symmetry. I can move it around and the design doesn't change. Focus. And graphs can have symmetry. The graph on the left has reflection and rotation symmetry, and on the right here we've got a graph with translation symmetry. If you want, you can get out some tracing paper and verify it. Woohoo! That's the end of our notes. I hope you all have a great day. Thanks for following along, and I'll see you in class. Bye.